Imagine standing on a bridge so high that clouds pass beneath your feet. Now picture that same bridge spanning a distance greater than 50 football fields. These aren't fantasies, they're real engineering marvels we'll be examining in our countdown of the world's 10 largest bridges. Bridges have come a long way from simple wooden planks across streams. Today, they're megastructures that push the boundaries of human engineering. These massive constructions connect continents, transform economies, and redefine what we thought possible in architecture and design. In this journey through the world's largest bridges, we'll explore incredible innovations and daunting challenges. From battling fierce winds to anchoring supports in treacherous waters, these projects showcase human ingenuity at its finest. But these bridges are more than just physical connectors. They're symbols of progress, uniting communities and driving economic growth on an unprecedented scale. Are you ready to discover the engineering feats that are reshaping our world? The story of bridges is as old as civilization itself. Our ancestors, faced with the challenge of crossing rivers and valleys, started with the simplest of solutions: fallen trees and stone slabs. But as human ambition grew, so did our bridges. The ancient Romans were among the first to perfect the art of the arch. Their stone bridges, like the Ponte Sant'Angelo in Rome, have stood for nearly 2 millennia. These early engineers discovered that the arch's curved shape distributed weight evenly, allowing for longer spans and heavier loads. Fast forward to the Industrial Revolution, and we see a quantum leap in bridge design. The development of iron and later steel changed everything. Suddenly, bridges could stretch further and rise higher than ever before. The iconic Brooklyn Bridge, completed in 1883, was a marvel of its time. Its steel cables and massive stone towers allowed it to span the East River, connecting Manhattan and Brooklyn in a way that transformed New York City. But the real game changer came with the advent of suspension bridges. By hanging the roadway from massive cables anchored at each end, engineers could create spans of unprecedented length. The Golden Gate Bridge, opened in 1937, pushed the boundaries even further. Its main span of 4,200 feet was a world record at the time, and it remains an enduring symbol of human achievement. As our understanding of physics and materials science advanced, so did our ability to build bigger and bolder. The development of press-dress concrete in the mid-20th century allowed for stronger, more durable structures. Computer-aided design revolutionized the planning process, allowing engineers to model complex forces and test designs virtually before breaking ground. New materials have also played a crucial role. Fiber-reinforced polymers, for example, are now used to create bridge decks that are lighter and more corrosion-resistant than traditional materials. And high-performance steel alloys allow for stronger, more flexible structures that can better withstand earthquakes and extreme weather. But it's not just about materials and design. Construction techniques have evolved dramatically too. Prefabrication allows large sections of bridges to be built off-site and then assembled in place, reducing construction time and minimizing disruption. And advances in foundation engineering have made it possible to build bridges in locations once thought impossible, like deep sea channels or unstable soil conditions. One of the most exciting developments in recent years is the use of smart technology in bridge design. Sensors embedded throughout the structure can monitor stress, vibration, and other factors in real time, allowing for predictive maintenance and improved safety. Some bridges are even being designed to adapt to changing conditions, with movable elements that can adjust to wind or traffic patterns. All of these innovations have culminated in a new era of mega bridges that push the boundaries of what we thought possible. These structures span vast distances, tower above cities, and connect entire regions. They're not just feats of engineering, they're reshaping economies and changing the way we live and work. When we think of bridges, we often picture them simply as structures that connect 2 points. But mega bridges are far more than that. They're economic lifelines that can transform entire regions. These massive projects don't just span physical gaps, they bridge economic divides, creating opportunities that were once unimaginable. Imagine a remote coastal town rich in natural resources but isolated from major markets. Now picture a mega bridge connecting that town to a thriving metropolis. Suddenly, goods can flow freely, commuters can access new job opportunities, and tourists can easily visit. This isn't just a hypothetical scenario, it's the reality for many communities touched by these engineering marvels. Take the Öresund Bridge, for example. This incredible structure connects Denmark and Sweden, effectively linking Scandinavia to Central Europe. Before its construction, traveling between Copenhagen and Malmö required a lengthy ferry ride. Now, it's a quick 35-minute drive. The result? A booming cross-border region with increased trade, a larger labor market, and new opportunities for cooperation and cultural exchange. But these benefits come at a staggering cost. Mega bridges often carry price tags in the billions of dollars. The Hong Kong-Zhuhai-Macau Bridge, for instance, cost an estimated $20 billion. That's more than the GDP of many small countries. With such enormous investments, it's natural to question whether these projects are economically viable. Critics argue that the costs often outweigh the benefits, pointing to examples of bridges to nowhere that failed to generate the promised economic boom. They contend that these massive expenditures could be better used for other infrastructure needs or social programs. Proponents, however, argue that the long-term economic benefits far outweigh the initial costs. They point to success stories like the Hangzhou Bay Bridge in China. This 22-mile-long marvel reduced travel time between Shanghai and Ningbo from 4 hours to just 2.5. The result? A surge in trade and commuter traffic that's estimated to generate billions in economic activity each year. Another compelling case is the Confederation Bridge, linking Prince Edward Island to mainland Canada. Since its opening in 1997, tourism on the island has increased by over 50%. The bridge has also significantly boosted exports, particularly for perishable goods like seafood, which can now reach markets much faster. These success stories highlight a crucial point: the true value of a mega bridge isn't just in its physical connections, but in the economic ecosystem it creates. By linking previously isolated areas, these structures can spark new industries, boost property values, and attract investment. They can turn sleepy towns into bustling hubs of commerce and innovation. However, it's important to note that not all mega bridges deliver on their economic promises. Factors like regional economic conditions, competing transportation options, and even geopolitical issues can all impact a bridge's success. The challenge lies in accurately predicting and maximizing these economic benefits while minimizing costs and environmental impacts. As we continue to push the boundaries of bridge engineering, the economic stakes grow ever higher. These projects aren't just about spanning physical distances, they're about bridging economic gaps and unlocking new possibilities for growth and development. Imagine standing at the edge of a chasm so wide and deep that the other side is barely visible. Now picture a bridge spanning that impossible gap, defying nature itself. This isn't fantasy, it's the reality of modern mega bridge construction. Take the Millau Viaduct in southern France, a bridge so tall that its highest point soars above the clouds. At 1,125 feet, it's taller than the Eiffel Tower. But height isn't its only challenge. The bridge spans a valley prone to strong winds and fog, making construction and daily operation a constant battle against the elements. So how do engineers overcome these seemingly insurmountable obstacles? The answer lies in a combination of innovative design, cutting-edge materials, and groundbreaking construction techniques. Let's start with the wind problem. The Millau Viaduct uses a streamlined deck design that allows air to flow smoothly around it, reducing wind resistance. Special sensors continuously monitor wind speeds and direction, allowing operators to adjust traffic flow or even close the bridge if conditions become too dangerous. But wind isn't the only natural force these mega bridges must contend with. Earthquakes pose a significant threat to bridges in many parts of the world. The engineers behind the Akashikaikyo Bridge in Japan, the world's longest suspension bridge, had to design a structure that could withstand the region's frequent seismic activity. Their solution? A flexible design that allows the bridge to move with the earth rather than against it. The main towers can sway up to 6.6 feet in any direction, while the bridge deck itself can move up to 28 feet horizontally. Deep waters present another set of challenges. The Hong Kong-Zhuhai-Macau Bridge, which spans 34 miles across the Pearl River estuary, required innovative solutions for its underwater sections. Engineers used enormous steel tubes to create artificial islands, which were then filled with soil and rocks to create stable foundations. These man-made islands serve as anchors for the bridge and house facilities like customs checkpoints. Prefabrication has revolutionized bridge construction, especially for projects in challenging locations. Large sections of bridges are now built off-site in controlled environments, then transported and assembled on location. This technique was crucial for the construction of the Öresund Bridge between Denmark and Sweden. The underwater tunnel section was built in segments on land, then floated out to sea and sunk into place. Giant floating cranes have become indispensable tools for mega bridge construction. These marvels of engineering can lift and place enormous bridge sections with incredible precision. The Asian Hercules one of the world's largest floating cranes, can lift up to 5,000 tons. That's like picking up the Statue of Liberty in its base. Safety and durability have also seen significant improvements. Modern bridges are equipped with an array of sensors that constantly monitor structural integrity, allowing for predictive maintenance and early detection of potential issues. Materials science has given us new, more durable concrete mixtures and corrosion-resistant steel alloys that can withstand decades of heavy use and harsh environmental conditions. These advancements have allowed engineers to push the boundaries of what's possible in bridge design. The Dangyang Kunshan Grand Bridge in China, for example, stretches for an astounding 102 miles across lowlands, rice paddies, and even a portion of Yangcheng Lake. It's a testament to how far we've come in our ability to overcome natural obstacles. Now that we've explored the incredible challenges and innovations behind mega bridge construction, it's time to unveil the top 10 largest bridges in the world. These structures aren't just marvels of engineering, they're testaments to human ambition and ingenuity. Let's start our countdown with number 10, the Vasco da Gama Bridge in Lisbon, Portugal. Spanning 12.3 kilometers over the Tagus River, this cable-stayed bridge is the longest in Europe. Its construction involved innovative techniques to combat the area's high seismic activity, including the use of flexible joints that allow the bridge to move up to 2 meters horizontally. At number 9, we have the Manchac Swamp Bridge in Louisiana, USA. This concrete trestle bridge stretches for 36.7 kilometers across alligator-infested swampland. What makes this bridge unique is its low-lying design, hugging close to the water to withstand hurricane-force winds that frequently batter the region. The 8th largest bridge is the Bang Na Expressway in Thailand. While it might look like a typical highway, this 54-kilometer elevated structure is actually the world's longest road bridge. Its construction used an impressive 1,800,000 cubic meters of concrete, enough to build 8 Hoover dams. Coming in at number 7 is the Donghai Bridge in China, connecting Shanghai to the Yangshan Deep Water Port. This 32.5-kilometer sea bridge had to overcome the challenge of being built in one of the world's busiest shipping lanes. Engineers developed a unique mobile cofferdam technique to minimize disruption to maritime traffic during construction. The 6th largest bridge is the King Fahd Causeway, linking Saudi Arabia and Bahrain. This 25-kilometer structure isn't just a bridge, it's a series of bridges and causeways with a border station in the middle. Its construction required creating 2 artificial islands and using over 350,000 tons of steel, more than 47 Eiffel Towers. Halfway through our list at number 5 is the Chesapeake Bay Bridge Tunnel in Virginia, USA. This 23-kilometer structure alternates between bridge and underwater tunnel sections, allowing large ships to pass overhead. The tunnel portions were built using a revolutionary immersed tube method, where prefabricated sections were sunk into a trench on the seabed. The 4th largest bridge is the Hong Kong-Zhuhai-Macao Bridge, a 55-kilometer marvel connecting 3 major cities in China's Pearl River Delta. This bridge tunnel system includes an underwater tunnel and 4 artificial islands. Its design had to account for typhoons, shifting seabeds, and the busy shipping routes of the South China Sea. Now we're into the top 3, where the scale and complexity of these bridges reach staggering levels. At number 3 is the Manchac Swamp Bridge in Louisiana, USA. This 36.7-kilometer concrete trestle bridge is built just a few feet above the water of the Manchac Swamp. Its low profile is designed to withstand hurricane-force winds, while its sturdy pillars resist the corrosive effects of the swamp water. The runner-up at number 2 is the Dangyang Kunshan Grand Bridge in China, part of the Beijing-Shanghai high-speed railway line. This bridge stretches an incredible 164.8 kilometers. Its construction involved driving over 10,000 pillars into the ground, some as deep as 80 meters. The bridge crosses rice paddies, canals, rivers, and even a lake, showcasing China's ability to overcome diverse geographical challenges. Finally, we've reached number 1, the largest bridge in the world. It's none other than the Changhua-Kaohsiung Viaduct in Taiwan. This colossal structure spans 157.3 kilometers, forming the backbone of Taiwan's high-speed rail system. What sets this bridge apart is not just its length, but its ability to withstand the frequent earthquakes that shake the region. The entire structure is built on massive shock absorbers that can move up to 1.5 meters in any direction, allowing it to flex and bend during seismic events. As we've seen, the world's largest bridges push the limits of engineering. Innovations in materials, design, and construction techniques have made these megastructures possible. But what's next? Engineers are already planning even more ambitious projects. The Strait of Gibraltar Bridge, if built, would span 14 kilometers between Europe and Africa. Meanwhile, China is considering a 123-kilometer bridge to connect Taiwan to the mainland. These proposals face enormous technical, financial, and political hurdles. Yet they show how mega bridges continue to captivate our imagination. These structures do more than connect places, they reshape economies, alter geographies, and redefine what we think is possible. As technology advances, who knows what incredible spans we might build in the future. The next generation of mega bridges may well make today's marvels look small by comparison.